Most galaxies are beautiful in the way that ordinary things are beautiful, consistent, familiar, reassuring in their predictability. A spiral galaxy is a spiral galaxy. You know what to expect when you look at one: the disk, the arms, the central bulge, the halo. An elliptical galaxy is an elliptical galaxy, a smooth, featureless spheroid of old stars, reddish gold, slowly rotating, serene. The universe, for all its vastness, runs on patterns. The same physical laws produce the same categories of structure across the 2 trillion galaxies of the observable cosmos. But the universe also produces anomalies, objects that refuse to fit the categories. Galaxies so unusual, so structurally bizarre, so extreme in some of their properties, that astronomers who first observed them genuinely struggled to explain what they were looking at. Galaxies that look like perfect rings with nothing at their center. Galaxies that are being torn apart by neighbors and yet are producing new stars at extraordinary rates. Galaxies that have black holes 1,000 times too large for their stellar mass. Galaxies so diffuse you can see through them to the objects behind. Galaxies embedded in sheets of stars that extend for hundreds of thousands of light years in directions perpendicular to their disk. These are the strange galaxies. Tonight, they are your bedtime stories. Take a slow, deep breath. Let your body sink into the surface beneath you. The strange galaxies are extremely far away, all of them. The nearest unusual galaxy worth naming is still millions of light years from Earth, and yet they are here, in the sense that their light arrives continuously, carrying their extraordinary appearances to the telescopes and eyes of the small planet that is curious about them. Let them come to you tonight, one by one, and carry you into sleep. Hoag's object is perhaps the most geometrically perfect and most mysterious galaxy known. It was discovered in 1950 by the astronomer Arthur Allen Hoag, who initially was uncertain whether it was a planetary nebula within our own Milky Way or something more distant. It is in fact a galaxy about 600 million light-years away in the constellation Serpens Cauda, and its appearance is so unusual that it immediately attracted attention and has retained it ever since. Hoag's object consists of a compact, yellowish nucleus of old stars surrounded by a nearly perfect ring of young, blue stars with a gap of dark space between the 2 components. The ring is almost circular. The nucleus is almost perfectly centered within the ring. The gap between them is real. There are very few stars in the space between the nucleus and the ring. If you were to encounter this galaxy without knowing what it was, you might think you were looking at a bullseye, or a cosmic eye, or a structure too geometrically precise to be natural. How Hoag's object formed is debated. One theory proposes that it formed through a head-on collision between 2 galaxies billions of years ago. When a small galaxy passes through the center of a larger one, the gravitational disturbance can create an outward expanding ring wave, similar to the ripples from a stone dropped into water. This ring of compressed material then triggers the formation of new stars. Another theory proposes it formed from a bar instability in an early disk galaxy, with the outer ring forming when material was expelled from the central regions. Neither explanation is fully satisfactory. The extraordinary symmetry of Hoag's object is made even more remarkable by what appears in one of the high-resolution images taken by the Hubble Space Telescope in the gap between the nucleus and the outer ring. At almost exactly the right position, another ring galaxy is visible in the background, millions of light years more distant. Whether this is coincidence or some kind of observational selection effect, it is one of the more aesthetically remarkable astronomical images in existence, a ring galaxy, seen through the gap of a nearer ring galaxy, both centered in the field of view. Ring galaxies, of which Hoag's object is the most famous, are a class of unusual galaxies that share the property of having a ring-like structure of star formation surrounding a relatively star-poor interior. The Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor, is another famous example. Unlike Hoag's object, the Cartwheel's origin is not mysterious at all. It was clearly created by a head-on collision with a smaller companion galaxy, which passed directly through the center of what was previously a normal spiral galaxy. The impact sent a ring of compressed material expanding outward like a ripple, triggering a wave of star formation. The ring of the Cartwheel Galaxy is one of the most intensely star-forming regions known, with a star formation rate estimated at several tens of solar masses per year. The James Webb Space Telescope's observations of the Cartwheel Galaxy, released in 2022, revealed the structure of its outer ring in extraordinary detail, showing a complex and dynamic system of star-forming knots and filaments that were not resolvable in earlier Hubble images. JUIC's infrared capabilities allowed it to penetrate the dust that obscures many of the star-forming regions in the outer ring, revealing the full extent of the starburst activity occurring in the aftermath of the ancient collision. The inner region of the Cartwheel shows complex, spoke-like structures connecting the nucleus to the outer ring, the gravitational aftermath of the violent encounter still playing out. Polar ring galaxies are among the most structurally peculiar objects in the universe. A polar ring galaxy consists of an ordinary-looking lenticular or elliptical galaxy surrounded by a ring of gas, dust, and stars that orbits perpendicular to the plane of the inner galaxy at or near the poles of the main galaxy's rotation axis. This is deeply unusual from a gravitational standpoint. In a normal galaxy, material settles into the equatorial plane. A perpendicular ring requires that the material have been acquired in some special way, with angular momentum nearly perpendicular to the main galaxy's angular momentum. The most famous polar ring galaxy is NGC 660, located about 44 million light-years away in the constellation Pisces. It has a strongly tilted inner disk and a prominent outer ring of material looping around the poles. Another well-studied example is NGC 4650A, which has a disk-like inner galaxy and a prominent outer ring at nearly 90 degrees to it. The accepted explanation for these structures is that the polar ring formed from material captured from another galaxy, either through a tidal interaction or an outright merger. The accreted material, having the wrong angular momentum to join the equatorial disk, settled instead into a polar orbit where it remains stable for billions of years. Polar ring galaxies provide a unique tool for measuring dark matter halos. In an ordinary galaxy, the mass distribution of the dark matter halo can only be probed in the equatorial plane through the rotation curve. A polar ring provides an independent measurement of the gravitational force along a perpendicular direction. By comparing the rotation curve of the polar ring with the rotation curve of the main galaxy, astronomers can determine the three-dimensional shape of the dark matter halo, whether it is spherical, flattened along the equatorial plane like the visible disk, or elongated along the polar axis. Observations of polar ring galaxies suggest that dark matter halos are not perfectly spherical, tending instead to be somewhat flattened. Interacting galaxies, pairs or groups of galaxies in the process of gravitational encounter, are among the most dramatic and visually spectacular objects in the extragalactic sky. When two galaxies approach close enough for their gravity to distort each other, the result is a complex and violent dance that can last for billions of years and ultimately transform both participants beyond recognition. The characteristic signatures of galaxy interaction include long tidal tails of stars pulled from the outer disks of both galaxies, rings of compressed material triggering new star formation, bridge structures connecting the two galaxies, and the eventual violent distortion of both disks into irregular, chaotic forms. The antenna galaxies, NGC 4038 and NGC 4039, located about 60 million light-years away in the constellation Corvus, are the nearest and most extensively studied pair of colliding galaxies. They get their name from the two long, curved tidal tails extending from the system, which in wide-field images resemble the antennae of an insect. The two galaxies began their encounter about 2 billion years ago, had their first close passage several hundred million years ago, and are currently interpenetrating each other's disks in what is expected to be their last close encounter before they merge completely into a single elliptical galaxy over the next few hundred million years. The ongoing collision in the antenna galaxies has triggered one of the most intense star formation events in the local universe. Thousands of new star clusters have formed in the compressed gas at the interface of the two galaxies, many of them extremely massive and dense, comparable to or exceeding the most massive globular clusters. Infrared observations of the system reveal enormous quantities of star-forming material heated by the young stars embedded within the interacting disks. The antenna galaxies are producing stars at a rate many times higher than the Milky Way, and the intense radiation from the newly formed massive stars is ionizing enormous regions of gas and creating a complex web of emission nebulae spread across hundreds of thousands of light years of the interacting system. Let your breathing be slow and peaceful. The antenna galaxies are 60 million light years away, but the light from their star formation reaches our telescopes and, in a sense, reaches this room. The idea of two galaxies interpenetrating each other, their stars passing through the enormous spaces between the stars of the other galaxy with virtually no direct collisions, is deeply calming, a collision of galactic scale that is, at the level of individual stars, entirely nonviolent. The two galaxies merge and transform, but their stars simply adjust their orbits over hundreds of millions of years, finding new equilibrium positions in the growing elliptical galaxy. The mice galaxies, NGC 4676A and NGC 4676b, located about 290 million light-years away in the constellation Coma Berenices, are another spectacular interacting pair. Their name refers to the long, thin tidal tails extending from each galaxy, which in telescope images resemble the tails of two mice. The tails are composed of stars pulled from the outer disks of both galaxies by the gravitational interaction. They will eventually fall back toward the merged galaxy over hundreds of millions of years, raining stars back onto the forming elliptical remnant. Stephan's Quintet, a compact group of 5 galaxies in the constellation Pegasus, provides a remarkable case study in galaxy interaction and its consequences. 4 of the 5 galaxies in the quintet are at a distance of about 280 million light-years and are physically interacting. The 5th, NGC 7320, is actually a foreground galaxy at only 40 million light-years, a chance alignment. The 4 genuinely interacting galaxies, NGC 7319, NGC 738A, NGC 7318b, and NGC 7319, show dramatic evidence of their long gravitational history, distorted morphologies, tidal debris spread across the group, a large shock-hated intergalactic medium produced by one of the galaxies plowing through the group at about 1,000 kilometers per second, and widespread star formation triggered by the interactions. Stephan's Quintet is one of the most observed compact groups of galaxies in astronomy and was among the first objects observed by the James Webb Space Telescope in its early science release of July 2022. The Jwest image of Stephan's Quintet revealed the complex structure of the shock-hated intergalactic gas in extraordinary detail, showing the turbulent, multi-temperature medium created by the high-speed intruder galaxy and tracing the filamentary structure of the interaction in ways not possible with previous instruments. Starburst galaxies are galaxies undergoing a period of extraordinarily intense star formation, much higher than their long-term average rate. The star formation rates in starburst galaxies can reach tens to hundreds of solar masses per year, compared to the Milky Way's rate of about 1 to 3 solar masses per year. This intense activity is usually triggered by a gravitational interaction or merger with another galaxy, which compresses the interstellar gas and drives it toward the galaxy's center, where it rapidly converts into stars. The intense radiation and stellar winds from the massive young stars, combined with supernovae explosions, can drive powerful outflows of gas from the galaxy, producing superwinds that extend for tens of thousands of light-years above and below the galactic disk. M82, the Cigar Galaxy, is the nearest and most famous starburst galaxy, located about 12 million light-years away in the constellation Ursa Major. It has been gravitationally disturbed by its companion M81, which passed close enough to compress the gas in M82's disk and trigger the current starburst. The central regions of M82 are forming stars at a rate about 10 times that of the entire Milky Way. The intense stellar feedback from this activity drives a spectacular superwind. Long streamers of glowing red hydrogen gas extend for about 10,000 light-years perpendicular to the galaxy's disk, visible in photographs as red rays shooting outward from both sides of the galaxy's cigar-shaped body. The outflow is moving at hundreds of kilometers per second and carries with it not just gas, but the products of stellar nucleosynthesis, enriching the intergalactic medium surrounding M82 with heavy elements. Ultraluminous infrared galaxies, or UARGs, are galaxies with infrared luminosities more than 100 times that of the Milky Way, produced by the re-radiation of absorbed starlight and AGN emission by enormous quantities of warm dust. They are always found to be major mergers of two or more galaxies, their star formation and AGN activity fueled by the enormous quantities of molecular gas driven to their centers by the merger process. The nearest ULERG is ARP 220, located about 250 million light-years away in Serpens, which has two merging nuclei embedded in a dense molecular cloud containing as much as 10 billion solar masses of molecular gas. The star formation rate in ARP 220 is estimated at several hundred solar masses per year, and the two nuclei are surrounded by compact radio continuum sources and intense maser emission. Active galactic nuclei, or ANG, are among the most energetic and extreme objects in the universe. They occur when the supermassive black hole at the center of a galaxy is accreting material at a high rate, converting a significant fraction of the mass energy of the infalling material into radiation. The luminosity of an ANG can exceed the combined luminosity of all the stars in its host galaxy by factors of tens to thousands. The brightest quasars, the most luminous class of ANG, have luminosities of 10 to 100 trillion times that of the Sun, making them visible across most of the observable universe. The energy production mechanism of an ANG is accretion onto the supermassive black hole. Material falling toward the black hole forms a disk due to its angular momentum, and friction within this disk heats the material to extreme temperatures and releases enormous quantities of electromagnetic radiation. The innermost regions of the accretion disk can reach temperatures of millions of degrees, producing X-ray and ultraviolet emission. The material spiraling inward through the disk loses gravitational energy, which is radiated away and ultimately falls across the event horizon. The conversion efficiency of mass to energy in an accretion disk around a rapidly spinning black hole can reach as high as 42%, compared to the 0.7% efficiency of nuclear fusion in stellar cores. Let your breathing be gentle. The quasars are burning at the centers of galaxies billions of light years away, pouring out a luminosity that staggers the imagination while you rest in the quiet of this room. They are not visible to the naked eye despite their extraordinary luminosity. Their distance is so great that they appear as faint points of blue shifted light in deep sky photographs. Each quasar is, at its heart, the same story: a massive black hole consuming material, releasing energy, illuminating its host galaxy from within. Seyfert galaxies are a class of active galaxies with relatively lower luminosity than quasars, named after Carl Seyfert, who described them systematically in 1943. They are nearby, low-luminosity ANG, whose host galaxy is clearly visible around the active nucleus, unlike quasars where the nucleus outshines the host galaxy completely. Seyfert galaxies are divided into two classes based on the width of their emission lines. Type 1 Seyferts have both broad and narrow emission lines, indicating they allow a direct view of the rapidly orbiting material close to the black hole. Type 2 Seyferts show only narrow lines, interpreted as Type 1 nuclei, viewed through an obscuring torus of dust and gas that blocks the direct view of the broadline region. This unified model of ANG, in which the same type of central engine produces the full range of ANG types depending on the viewing angle and the obscuration by the surrounding dust torus, is one of the great simplifying insights of extragalactic astronomy. What appears as a quasar, a Seyfert 1, a Seyfert 2, a radio galaxy, or a narrow-line radio galaxy may all be the same fundamental object seen from different directions. The apparent diversity of Ang types reflects the geometry of the obscuring material and the orientation of the relativistic jets, not fundamental differences in the central engine itself. BL-lac objects and blazars are Ang whose relativistic jet is pointed almost directly at Earth. This alignment has several dramatic consequences. The jet emission is highly Doppler boosted, appearing far more luminous than it would from a different viewing angle. The variability of the source is rapid and extreme, changing on timescales of minutes to hours, and the optical emission is dominated by the synchrotron radiation from the jet, rather than from the accretion disk, producing a featureless, blue-white continuum without the emission lines that characterize most Ang. BL-lac objects were initially so confusing that they were classified as variable stars before their extragalactic nature was recognized. Centaurus A, located only about 13 million light-years away in the southern constellation Centaurus, is the nearest radio galaxy and one of the most extensively studied active galaxies. It has a massive supermassive black hole of about 55 million solar masses at its center, surrounded by a brilliant jet of relativistic plasma extending from the nucleus outward for about 4,000 light-years in the visible band and much further in the radio band. The galaxy itself has the appearance of a giant elliptical galaxy with a dark, warped dust lane running across its middle, the remnant of a spiral galaxy that was absorbed by the elliptical some hundreds of millions of years ago. The dust lane is rich in young blue stars forming in the compressed gas at the edge of the lane, an ongoing starburst triggered by the ancient merger. NGC 1277, a compact lenticular galaxy in the Perseus cluster about 220 million light-years from Earth, hosts one of the most extreme supermassive black holes known relative to its host galaxy. The black hole has a mass estimated at about 17 billion solar masses, which is about 59% of the total mass of the galaxy's bulge. In a typical galaxy, the black hole mass is about 0.1 to 0.5% of the bulge mass. NGC 1277's black hole is roughly 200 to 400 times too massive for its host galaxy under this relation. If our own Milky Way had a black hole this large in proportion to its stellar mass, Skrar A would have a mass of several hundred billion solar masses rather than 4 million. The explanation for NGC 1277's extreme black hole is unclear. It may have formed its black hole extremely rapidly in the early universe, or it may have grown through a series of mergers that preferentially added mass to the nucleus. Shell galaxies are elliptical galaxies surrounded by faint, concentric shells of stars, visible in very deep photographic exposures as arcing structures of varying brightness wrapped around the central body of the galaxy. They are the signatures of past mergers, when a smaller galaxy falls into a larger one on a nearly radial orbit. Its stars oscillate back and forth through the larger galaxy's potential, piling up at the turning points of their orbits to create the characteristic shell structures. The shells can persist for billions of years after the merger, gradually phase mixing and smoothing out over cosmic time. NGC 474, an elliptical galaxy about 100 million light years away, has some of the most spectacular shell structures known, visible as a complex system of interleaved arcs surrounding the central galaxy. Ultra-diffuse galaxies are among the most surprising categories of galaxies discovered in recent decades. They have the physical extent of a normal large galaxy, comparable in size to the Milky Way, but with surface brightnesses 100 to 1, 0 times fainter than a typical galaxy of the same size. The first ultra-diffuse galaxies were found in large numbers within the Coma Cluster in 2015, when a systematic search of deep imaging revealed hundreds of large, faint blue objects scattered throughout the cluster. Since then, thousands of ultra-diffuse galaxies have been found in galaxy clusters and in the field. The nature of ultra-diffuse galaxies is debated. Some appear to be almost entirely devoid of dark matter. The galaxy Dragonfly 44 was initially reported to be a mostly dark matter galaxy with very few stars, but subsequent analysis revised its properties toward a more star-dominated system. In contrast, NGC 1052 DF2 and NGC 1052 DF4 appear to be unusually dark matter-poor galaxies, with stellar kinematics suggesting they are supported by the motions of their stars rather than by a dark matter halo. This is deeply puzzling. Standard galaxy formation models expect all galaxies to form within dark matter halos, and a galaxy with essentially no dark matter challenges our understanding of how galaxies form. Various explanations have been proposed, including formation through tidal stripping of a larger galaxy's outer regions, or formation from the material ejected by high-speed galaxy encounters. Let your mind drift gently. The ultra-diffuse galaxies are out there in the Coma Cluster, enormous but almost invisible, barely brighter than the sky background. Their sparse stars spread across a volume comparable to the Milky Way. They are galaxies that have somehow formed with very few stars relative to their size, perhaps failed galaxies, or galaxies that lost most of their star-forming gas before it could be converted into stars. Compact elliptical galaxies are the opposite extreme. Tiny, dense spheroids of stars with stellar densities far higher than normal elliptical galaxies. The most famous example is M32, a compact elliptical satellite of the Andromeda Galaxy located about 2.5 million light-years away. M32 has a stellar mass of about 1 billion solar masses packed into a radius of only about 1,000 light-years, giving it a central stellar density comparable to that of a globular cluster. M32 is thought to be the stripped core of a once larger spiral or elliptical galaxy, whose outer regions were tidally removed by its long interaction with the far more massive Andromeda Galaxy. Irregular galaxies are those that resist classification into the standard categories of spirals and ellipticals, displaying chaotic or asymmetric morphologies produced by gravitational interactions, ongoing merger processes, or simply insufficient mass to develop a regular structure. The most famous examples are the Large and Small Magellanic Clouds, the satellite galaxies of the Milky Way visible from the southern hemisphere. Both are rich in gas and ongoing star formation, including the spectacular Tarantula Nebula and the Large Magellanic Cloud, but neither has the symmetric disk or bulge structure of a spiral galaxy. Their irregular appearance is partly a consequence of the tidal forces of the Milky Way and their mutual interactions. Zwicky 18, a dwarf irregular galaxy about 60 million light-years away in Ursa Major, is one of the most chemically primitive galaxies known in the local universe. Its heavy element content is less than 3% of the solar value, meaning it has undergone very little nucleosynthetic enrichment by stellar generations compared to most local galaxies. For decades, Zwicky 18 was believed to be an extremely young galaxy, possibly still in its first epoch of star formation. However, subsequent infrared observations with Hubble revealed a population of old red stars in the galaxy that must be several billion years old, indicating that the galaxy formed long ago but has had an extremely low rate of star formation for most of its history. It is ancient but chemically virginal, having converted so little of its gas into stars that its chemical composition remains close to the primordial. The Sombrero Galaxy, Messier 104, is one of the most recognizable galaxies in the sky, visible with a small telescope and appearing in photographs as a nearly edge-on spiral galaxy with a prominent, wide dust lane running along its equator and a brilliantly glowing central bulge that gives it the appearance of the Mexican hat for which it is named. Located about 31 million light-years away in Virgo, the Sombrero has an unusually large and bright central bulge compared to its disk, and its dark lane of dust is exceptionally pronounced. The Sombrero also contains one of the largest populations of globular clusters of any nearby galaxy, with an estimated 1,200 to 2,000 globular clusters orbiting in its halo, far more than the Milky Way's approximately 200. The Sombrero's supermassive black hole, estimated at about 1 billion solar masses, is among the most massive in any nearby galaxy, making it about 250 times more massive than the Milky Way's Skrar A. The black hole is quiescent at present, not accreting material at a significant rate, but its mass reveals a past history of active growth. The Sombrero may be a somewhat unusual galaxy in transition between a spiral and an elliptical, having used up much of its star-forming gas and now containing a large population of old stars and an oversized bulge with only a relatively modest disk of remaining star-forming material. Markarian galaxies are galaxies with unusual ultraviolet brightness identified in a systematic spectral survey conducted by the Armenian astronomer Benjamin Markarian in the 1960s and 1970s. The Markarian catalog, which contains over 1,000 objects, includes Seyfert galaxies, starburst galaxies, blue compact dwarf galaxies, and other unusual systems whose excess ultraviolet emission distinguishes them from normal galaxies. Markarian 231 is the nearest quasar at about 600 million light-years and is a Ullrich that is also classified as both a starburst galaxy and a Type 1 Seyfert. It shows evidence for a massive molecular outflow driven by the combined feedback from star formation and the Ang, with gas being expelled from the galaxy at a rate of several hundred solar masses per year. The ARP Catalog of Peculiar Galaxies, compiled by Halton ARP and published in 1966, contains 338 unusual and disturbed galaxies that did not fit the standard morphological categories. ARP assembled the catalog deliberately as a challenge to the existing understanding of galaxy morphology and evolution, presenting objects that seem to require explanations beyond simple gravitational dynamics. The catalog includes interacting pairs, galaxies with large companions, galaxies with small companions attached by bridges, chains of galaxies, galaxies with diffuse countertails, and many other peculiarities. The ARP catalog has been an invaluable resource for studies of galaxy interaction and has inspired decades of follow-up observations. ARP 87, a pair of interacting galaxies about 300 million light-years away, shows a spectacular bridge of stars and gas connecting a spiral and a large elliptical, a delicate luminous thread spanning about 75,000 light-years of intergalactic space. This bridge formed through the gravitational interaction of the two galaxies and is populated by young stars formed in the compressed gas of the bridge itself. ARP 87 is sometimes described as galaxies kissing, connected by this fragile bridge, even as they continue to drift apart from each other. Let your breath settle into silence. The strange galaxies are all out there right now. The perfect ring of Hoag's object with its mysterious precision, the exploding starburst of M82, sending superwinds into intergalactic space, the merging antennae creating thousands of new star clusters in the violence of collision, the ultra-diffuse ghosts barely visible against the sky background, the massive sombrero with its extraordinary globular cluster population, and Centaurus A with its relativistic jet carving through the medium around it. The universe still has more strange galaxies to introduce. Some of the most remarkable are yet to come. Lenticular galaxies, classified SO in the Hubble morphological sequence, sit at the boundary between spirals and ellipticals. They have the disk and bulge structure of a spiral, but have lost most or all of their star-forming gas, so the disk is smooth and featureless, without the spiral arms and high regions that characterize ordinary spirals. They represent galaxies in transition, former spirals that have been stripped of their gas by ram pressure in galaxy clusters, or have consumed their gas supply through past star formation. The Sombrero Galaxy may be a lenticular, or at least a galaxy trending toward that category. The large number of lenticulars in the centers of rich galaxy clusters suggests that the cluster environment plays a significant role in their formation through ram pressure stripping. Compact groups of galaxies, small associations of 3 to 8 galaxies in a physically dense configuration, are environments of intense and prolonged gravitational interaction. Hickson compact groups, cataloged by Paul Hickson in 1982, are among the most extensively studied such configurations. The members of a compact group are sufficiently close that their mutual gravitational interactions occur on timescales of only billions of years, leading to strong tidal distortions, gas stripping, and eventually mergers among the members. Compact groups are thought to be precursors to the formation of a single giant elliptical galaxy, the accumulated product of all the mergers that proceed within them. CD galaxies, or brightest cluster galaxies, are the most massive and luminous galaxies in the universe. They sit at the centers of rich galaxy clusters and have grown to their enormous sizes through the accretion of dozens of smaller galaxies over cosmic time. What distinguishes CD galaxies from other giant ellipticals is their extended stellar halo, a diffuse cloud of stars that can extend for hundreds of thousands or even millions of light years around the central body of the galaxy. This stellar halo is the accumulated debris of all the galaxies that have been tidally stripped or merged with the central galaxy over billions of years. NGC 6166 and the Able 2199 galaxy cluster, located about 450 million light-years away in Hercules, is one of the most spectacular CD galaxies known. It has at least 5 nuclei visible in its inner regions, the remnants of distinct smaller galaxies that fell into the center and are in the process of merging. Its stellar halo extends for about 750,000 light-years, nearly as large as the entire local group. The total stellar mass of NGC 6166 is estimated at about 1 trillion solar masses, 5 to 10 times that of the Milky Way. If you could see NGC 6166 from the distance of the Large Magellanic Cloud, its stellar halo would cover most of the visible sky. IC 1101 is the largest known galaxy, a giant CD galaxy at the center of the Abell 2029 galaxy cluster, located about 1.07 billion light-years away. Its extent has been measured at roughly 4 to 6 million light-years across, more than 50 times the diameter of the Milky Way. If our solar system were at the edge of IC 1101 and we tried to travel to the center at the speed of Voyager 1, approximately 17 kilometers per second, the journey would take about 100 trillion years, roughly 7,000 times the current age of the universe. IC 1101 contains an estimated 100 trillion stars, hundreds of times the estimated number in the Milky Way. It is a monument to billions of years of galactic cannibalism at the center of a rich cluster. The Tadpole Galaxy, UGC 10214, is a disrupted barred spiral galaxy about 420 million light-years away that presents one of the most dramatic examples of tidal distortion in the local universe. A compact intruder galaxy plowed through the outer regions of the tadpole at high speed, and the gravitational interaction pulled a spectacular tidal tail from the main disk. The tail extends for about 280,000 light-years, nearly 3 times the diameter of the Milky Way, and is dotted with blue knots of newly formed star clusters, regions of compressed gas where star formation was triggered by the tidal compression as the material was pulled from the main galaxy. The intruder galaxy that caused this damage is visible in the upper left of Hubble images as a small compact galaxy, looking entirely innocent of the havoc it caused. Head-tail and wide-angle tail radio galaxies are among the most visually striking objects revealed by radio telescopes. These are galaxies with active nuclei producing relativistic jets, but whose jets have been bent and swept back into dramatic arc, like or sweeping tail structures by their motion through the dense intracluster medium of the galaxy cluster in which they reside. As the galaxy moves through the cluster gas at hundreds or thousands of kilometers per second, the ram pressure of the cluster gas sweeps the jets behind the galaxy, creating a curved, swept back morphology that looks like the wake of a moving boat or the bent feathers of a bird in flight. Wide-angle tail radio galaxies, sometimes called bent double radio sources, have their jets bent into a wide U or V shape. Their morphology is so distinctive that they can be used to identify galaxy clusters at high redshift. Finding a wide-angle tail radio source in a survey almost always indicates the presence of a surrounding cluster. Galaxy downsizing is one of the most significant patterns in the evolution of galaxies across cosmic time, and it is deeply counterintuitive. Standard models of structure formation in a universe dominated by cold dark matter, predict that small structures form first and large structures form later through the hierarchical merging of smaller systems. Stars should therefore form in small galaxies first and in large galaxies later. But observations show the opposite. The most massive galaxies appear to have formed most of their stars earliest, at cosmic noon or even before, and have been passive and quiescent ever since. Smaller galaxies form their stars more slowly and have more sustained star formation over cosmic time. The most massive galaxies were fully assembled and dead before many smaller galaxies had formed even a fraction of their eventual stellar population. This downsizing pattern is one of the unresolved tensions in galaxy formation theory. Various mechanisms have been proposed to explain it, including the intense Ang feedback from the powerful quasars that inhabited the most massive early galaxies, which heated or expelled the gas and shut down star formation. The dense environments of protoclusters where the most massive galaxies formed, which may have exhausted the local gas supply through intense early star formation, and the deep gravitational potential wells of the most massive halos, which made it difficult for new gas to cool and form stars once the initial burst was complete. None of these explanations is fully satisfactory, and the downsizing problem remains a challenge for models of galaxy formation. The Dragonfly Telephoto Array, a telescope system consisting of an array of commercially available camera lenses combined to achieve a very low surface brightness sensitivity, has revealed a hidden population of ultra-diffuse and faint stellar structures around nearby galaxies that were previously invisible to conventional telescopes. Its images of galaxies like NGC 1052, M101, and others have revealed extended stellar halos, faint streams of tidally disrupted satellite galaxies, and diffuse structures stretching for hundreds of thousands of light years around nearby galaxies, demonstrating that the outskirts of galaxies are far richer in faint material than was previously appreciated. The Dragonfly Array has essentially created a new observational window into the low surface brightness universe. One of the most puzzling populations of objects discovered in the modern era of galaxy surveys is the compact, massive galaxies found at high redshifts of 2 to 3, corresponding to times when the universe was only 2 to 3 billion years old. These galaxies have stellar masses comparable to the most massive elliptical galaxies today, but they are physically much smaller, with effective radii 3 to 10 times smaller than equally massive local ellipticals. They appear to be fully formed, fully quiescent, metal-rich old stellar systems that somehow assembled their enormous stellar masses, shut down all star formation, and settled into a compact configuration, all within the first 1 to 2 billion years after the Big Bang. How they grew from these compact seeds into the diffuse, extended ellipticals we see today, without forming significant numbers of new stars, is one of the central questions of modern extragalactic astronomy. The most widely accepted mechanism is the accretion of many small satellite galaxies through minor mergers over billions of years, which adds stellar mass to the outskirts of the compact galaxy, gradually building up the extended envelope we observe today. Let your breathing settle to its softest, most natural rhythm. The strange galaxies are out there in their millions of flavors, ringed and rippled and colliding and active and diffuse and compact and shrieking with star formation and silent for billions of years. Each one is a separate story, a separate universe of events and processes occurring at a scale that dwarfs any human reference point. And yet each one is governed by the same physical laws that govern the chemistry of your body and the orbit of your atoms. The strangeness of galaxies is in the end the strangeness of the universe expressing itself. The same gravity that holds you to the surface of the Earth holds galaxies together across hundreds of thousands of light years. The same nuclear physics that powers the sun powers the quasars at the centers of distant galaxies. The same quantum mechanics that determines the behavior of atoms in your cells determines the behavior of electrons in the plasma of relativistic jets. Everything is connected through the laws of physics that operate identically everywhere in the observable cosmos. Each of these objects tells a different part of the story of how galaxies form, evolve, interact, merge, and die. Each one is an experiment run by the universe at a scale that dwarfs anything human civilization will ever construct. And the results of these experiments are written in the light arriving at our telescopes, photon by patient photon, from distances measured in millions and billions of light years. The universe has been running these experiments for 13.8 billion years without pause. It has tried every possible combination of mass and angular momentum and environment and merger history and black hole mass and dark matter distribution, and the result is a zoo of galaxies so diverse and strange that astronomers have spent generations cataloging and classifying and explaining only a fraction of what exists. Every deep field image reveals new morphological types, new edge cases, new objects that prompt new questions. You do not need to hold all of this in your mind tonight. You only need to know that the strange galaxies exist, that they are real, that they were there when the light now reaching our telescopes was emitted and have been there ever since, quietly undergoing their extraordinary processes while the universe expanded around them. The collision of the antennae was happening 60 million years ago when the light you observe was emitted. The starburst of M82 was blazing 12 million years ago. Hoag's object was perfectly ringed 600 million years ago. All of this is old news, arriving only now at a quiet planet where curious beings have built instruments sensitive enough to receive it. Let your body be completely still. Let your thoughts be gentle and dispersed, like the diffuse stars of an ultra-diffuse galaxy spread across a great space with no particular urgency to concentrate. The strange galaxies are doing their extraordinary things far away, in the dark, in the silence of intergalactic space. And you are here, breathing slowly, in the warmth of a small room on a small planet, drifting peacefully toward sleep. The universe is generous with its strangeness. It has made objects that break every expectation, galaxies that should not exist by the rules that seem to govern everything else, structures of inexplicable precision and structures of beautiful chaos, all of them patient, all of them distant, all of them quietly illuminating the darkness with their ancient light. Tonight, they are your companions. Let them carry you into rest. The universe has one more category of strangeness to offer before sleep arrives fully. Intracluster light is the diffuse glow of stars that have been stripped from their parent galaxies and now drift freely through the space within a galaxy cluster, not belonging to any single galaxy. These stars, liberated by billions of years of tidal interactions and mergers within the cluster, form a faint luminous envelope permeating the entire cluster volume. The intracluster light is extremely faint, typically less than 1% of the sky background brightness, making it extraordinarily difficult to detect and measure. But modern deep imaging surveys have revealed that intracluster light can account for 10 to 40% of the total stellar mass in a rich galaxy cluster, an enormous reservoir of stars that is not cataloged in any galaxy but exists in the interstices between them. The stars of the intracluster light are among the most isolated stars in the universe. They orbit within the gravitational potential of the cluster as a whole rather than around any individual galaxy, on orbits that take them billions of years to complete. They spend most of their lives in a region of space where the nearest neighboring star is dozens or hundreds of light years away, in complete isolation from any galactic structure. If a planetary system exists around any of these wandering stars, its inhabitants would look out at a sky almost entirely devoid of the Milky Way band that defines our night sky, seeing instead the diffuse glow of other galaxy cluster members scattered across hundreds of degrees, a sky of galaxies rather than a sky of stars. The most isolated galaxies in the universe are the so-called field galaxies that reside in cosmic voids, the enormous, nearly empty regions of space between the filaments and walls of the cosmic web. A void galaxy may have no significant galactic neighbors within tens of millions of light years in any direction. In this isolation, they evolve entirely through internal processes. There are no tidal distortions, no stripping events, no mergers to complicate their development. They evolve slowly, quietly, consuming their gas reserves and forming stars at a gentle pace, entirely determined by their own initial conditions and internal physics. The void galaxy VG's 31b was identified by the Void Galaxy Survey as a spiral galaxy residing deep inside the Eridanus void, one of the largest known voids in the local universe. Its lack of environmental interactions has allowed it to maintain an unusually regular and undisturbed morphology, a nearly perfect spiral with no signs of the tidal distortion or asymmetry that characterizes most real spirals shaped by their environment. It is what a spiral galaxy looks like when the universe leaves it entirely alone for billions of years. A pure expression of internal galactic dynamics, uncomplicated by neighborhood. As the universe continues to expand and dark energy drives galaxies beyond the horizon of cosmic accessibility, the isolation of individual galaxies and galaxy groups will increase inexorably. In the very distant future, billions of years from now, the local group, the collection of galaxies, including the Milky Way and Andromeda and their satellites, will be the only visible structures within our observable universe. All other galaxy groups will have receded beyond the Hubble horizon, their light redshifted to immeasurably long wavelengths, unreachable and undetectable. Our descendants, if any survive. We'll look out at a sky containing only the stars and galaxies of the local group, surrounded by absolute darkness in every other direction. They will be unable to discover the expansion of the universe through galaxy recession measurements, unable to observe the cosmic microwave background in any form, unable to see the evidence that their galaxy was once part of a vast cosmic structure stretching across billions of light years. The strange galaxies, too, will eventually be lost to view. Hoag's object will recede beyond our horizon. The antennae will complete their merger, and their elliptical remnant will drift away. IC 1101 will become unreachable light, its 100 trillion stars invisible. The universe is creating, right now, the conditions under which its own history becomes unreachable to future observers. We live in a privileged epoch. The universe is old enough that its large-scale structure is clearly visible, but not so old that accelerating expansion has swept the evidence away. Let your body be completely still. Let your thoughts be gentle and dispersed, like the diffuse stars of an ultra-diffuse galaxy, spread across a great space with no particular urgency to concentrate. The strange galaxies are doing their extraordinary things far away, in the dark and the silence of intergalactic space. And you are here, breathing slowly, in the warmth of a small room on a small planet, drifting peacefully towards sleep. The universe is generous with its strangeness. It has made objects that break every expectation, galaxies that should not exist by the rules that seem to govern everything else, structures of inexplicable precision and structures of beautiful chaos, all of them patient, all of them distant, all of them quietly illuminating the darkness with their ancient light. Tonight, they are your companions. Let them carry you into rest. Sleep now. The strange galaxies will still be there when you wake, still ringed, still merging, still blazing, still diffuse, still extraordinary. Good night.